welcome to a video about references and pointers. This is a C++ fundamentals video that's going to demonstrate something that you're probably going to encounter quite a bit in your journey while C++ programming. Let's get started by making a new project here. I'm going to call it circles because we're going to use circles to demonstrate today's tutorial. First thing I'm going to do is make a new header for the OLC Pixel game engine. I do like using the OLC Pixel game engine, as I've probably demonstrated on the channel quite a bit now. So I'm just going to grab that from the repo real quick. We'll always leave a description, or the engine in the description in case you can't find it yourself. And I'll create a new circles.cpp file to represent our game today. With any OLC Pixel game engine project, I like to start with the Pixels demo, which is already included in the header file itself. And nice, I pasted it and it even auto-formatted it for me. That's very good. So I'm just going to change the title of the window to be Circles Example. I'm also going to refactor the class name example here to be Circle Example, just to customize the project ourselves a little bit. And let's just make sure it runs. Excellent, as always. Today, to demonstrate references and pointers, I'm first going to create a list of circles. We don't have a circle class right now, but essentially it's just a point and a radius. So I'm going to create a struct called circle, and circles will contain an OLC 2D float vector called position, and one float for its radius. Since it's a struct, circle list. We'll have to define the circle list out here so that we can actually keep it in memory. I'm going to make a for loop, iterating 5 times in one direction and 5 times in another. That's why I'm using the x and y parameters here. Inside circle list, I'm going to push back some new circles. Since this is a struct, I'm going to use the initializer list list constructor, and I am going to populate it, each one with a position and a radius based on its x and y. So for the position, that requires an initializer list for itself since it's 2 parameters. I'm going to fill it in with x times 16, comma y times 16, and then followed by a radius. In this case, I think I'm going to make the radius be 8 pixels large for each circle. And there we go. This will push a new circle into the list 25 times. In order to see our circles, let's iterate through them. First, I'll clear the screen using clear. And we'll clear the screen to, let's do a very dark green today. Let's change it up. I will now iterate through every circle for circle C inside of circle list. That's how you read this. I'm going to say draw circle. Specify a position, which is currently a float, but you can see I'm referencing a new circle, so it gets stored in C. So if I type the dot, I also get a position and a radius. In this case, we want the position, although we probably have to convert it to an integer. It might do it itself. We'll find out in a second. C.radius. The defaults are draw a white circle and draw all the edges of it. So it says no overloaded function could convert all the argument types. for a circle list allocator. Really now. I'll go ahead and be explicit here and say this is a VF2D. And now there's a narrowing conversion error, as I kind of suspected, at line 26. So these are probably considered integers by default. We'll transform them into floats by making one of the parameters a float. That way a float times an integer gets us that. I did forget the circles start centered, so let me move them down a little bit, just give them all some little offset. VF2D, draw offset. Let's set it to 64, 64. One cool thing you can do is add two vectors together. So we can add the position to the draw offset. The math should work itself out. There we go. We have our circles. This will be our example today when we talk about references and pointers. So let's talk about what we did real quick. We iterated through circle list and grabbed a copy of each circle, and drew them. How do I know these are copies? Well, I can tell just from the syntax. But if these really are copies, there should be a way to prove that, right? There are two ways we can prove it. I'll do the easy one first. The easy way to prove it is to try to change the circle's position permanently. Let's say in our code, if we iterate through every circle and they were not copies, as in they were direct references to the circles, then modifying their position should cause their position in the future to change, right? Like you would expect. I'm actually going to do this in the onUserCreate function, so it only happens one time. If we made all of our circles, and then we adjusted every single circle's position, let's add 32 by 32 to every position. Actually, that'll make it hard to tell what's going on. Let me do 0, 300. Something ridiculous, right? If I do this, then we should expect that all the circles go off screen. 300 is a pretty large number in our example. But if I run the example, it looks like nothing's changed. In effect, it looks like this didn't even work. And the reason for that is because when you don't, or when you use this syntax, you're actually creating a new copy. Another way we can prove this is by creating an explicit constructor in our struct, where we define, let's say, a position and a radius. This would be done by default normally. And here we're going to initialize the parameters for said constructor. And inside our constructor, I'm just going to add one message that says circle created. Now, if this worked, if we assumed that we were only creating 25 circles, this line should display 25 times. However, as you see in a moment, that will not be the case. Let me run it. So here's our window, and here's our console. Now, all of these amount to, let's see, 33 lines. Or, excuse me, not 33 lines. Let me put this in a place where it's not in the way. New text file, please. Alright, 25 lines. Okay, well, that's all well and good. Circle created. So what's the deal with not changing these then? Well, we're not actually using this constructor when we're copying something. We're actually using a different constructor. It's called the default copy constructor, I believe. And normally this would look like I want to say something like this. I'll have to double check that. Copy constructor CPP C++. The copy constructor, I'm going to go here. If we look here, there is a const class name and const class name and. So it looks like this. This is your copy constructor. And if this is called, then that would be a copy. I should have left the other constructor, actually. I wanted to demonstrate how this works here. So I'm actually going to make another constructor. This is our copy constructor. And by default, according to CPP reference, this is syntax for it. So let me go ahead and add this in. So you'll see the console is actually being spammed with circle copied right now. And yeah, it's gone so far that I can't even see the circles that were created. This is what I wanted to demonstrate with copying constructors. So our issue right now is that circles are continuously being created every single loop and iteration. Knowing this, and knowing these are creating copies, what do we do to fix that? Well, it's as simple as using this operator right here, the ampersand. If I replace the space with an ampersand, and some folks like to add a space after because, you know, just tidying things up, and run this again, we'll see that we get slightly different results. We'll also see the screen is now blank. So first, what happened was we created a circle, and then we copied a circle. Create, copy, copy. Create, copy, copy, copy. Create, copy, 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 copy. You see these copies are like adding up on themselves, I guess you could say. You might think, huh, that's a little strange, right? Where are we copying, and what are we copying to? Well, let's think about the circle list and how we used it real fast. This right here creates a new circle. I could just move this into a separate line here and call it my circle or something, right? And if we have my circle here and we're trying to push back into it, what are we essentially doing? We're saying create a circle here and then push it back into this list. But what does pushing back into a list really mean? Pushing back into a list would basically take this circle we created and create a copy of it, and that copy goes in the list. So it's not necessarily a reference. So we can also prove this. Let me hide this code for now. So just to show you what I mean. If I hide this code and rerun the program, now we'll see the circles are back here, which makes sense. We removed the code that dropped them down a bunch of lines. The next thing I'll do is after I push a new circle into the list, I'm still using the same object here. I'm going to modify the position 0, 300, kind of like I did in the loop down there. So this my circle position is going to go down by 300. But the my circle we pushed into the circle list, as you'll see in a second here, is a different circle. Look at that. We didn't actually touch the my circle inside the list. We just modified the local my circle inside of the scope here. So the reason why we're seeing all these copies is every time we create a circle, we're copying a new circle into the circle list. And you'll actually see we're copying a lot of circles eventually. This amount of copying is happening whenever the vector reallocates. So, as you know, or hopefully you know, vectors will naturally expand themselves every once in a while. And every time they have to expand themselves, they have to take every copy or every object and recopy their contents into a new place of memory. That way they can continue to grow. So you'll see here at first we copied over. You can ignore the first copy, that's just copying into the list, but every time we reach a certain size, we have to recopy all the contents over to a new place of memory. So after a while, the list ends up adding a couple. So circle created, circle copied, just one circle copy for a while. Then it's like, oh, the list is too big, let's expand it out more. Then we can add some more elements, and then pretty soon it gets too big, so it gets copied again. Create, and eventually copy. And this goes on forever and ever as you keep expanding the list. So now you can start to understand a little bit of the inner workings of how vectors work and object copying works, which is rather fascinating. And this syntax right here now means you want a direct reference to whatever's in the list. So from here on out, if you use this operator, then you're getting the object directly. You're not getting a new copy. So when we ran this code and the circles were not on screen, that's because in the onUserCreate function, we pushed them 300 pixels down. I'm gonna get rid of this now. So if these are references, what is a reference exactly? A reference is just a pointer in memory. So if I were to go through every circle here and output its location in memory, so I would just write an ampersand followed by a C, and this will give me the pointer to that object. So you can think of this first one as being a reference. Don't copy, just a reference, because it's part of its type. Like, we can try to think of this as just one thing. This is its type. It's a circle reference. But here, this is an operator. This is the indirection operator. And so what we're saying is take the memory address or reference, or yeah, I should say memory address here, of whatever element we provide. So this is a direct reference to a circle. So it's a circle, but it just happens to be pointing to the same place as the circle we get from circle list. Now we're getting the address of that. So if I just output all these addresses, you'll see here we just get a bunch of hexadecimal numbers, which is what we would expect. They're addresses in memory. And for the most part, they're contiguous, not necessarily, because every time we expand, they probably get messed up a little bit. But they might be contiguous, actually. I'm not really willing to do the math here right now, but it's the bit math. Anyway, so those are our memory addresses, and every time we move them over, they get new addresses, by the way, because they're new copies, essentially. But we can see there that all of them get unique addresses. But what happens when we used this? So we compare this list and the addresses of them, and this list to the addresses of them. So first I'm going to print out, or I'm going to iterate through the circle list with copies and print the addresses of them. And then I'll put a giant bar here. And then I'll print out all the addresses of the reference circles. So this is an interesting thing I discovered while I was first working with the references for the first time and didn't really understand them, is you'll actually see the same address being used over and over. And that kind of makes sense if you think about it. If we're iterating through every circle and creating a new copy of it, but then we destroy it right after. Like, once we're out of the scope and we're onto the next iteration of this loop, we essentially don't need that circle anymore. It's gone out of scope. So what C++ does is it reuses this address over and over for different circles. So you can see the circle gets copied, and then here's all of our addresses. And they're all the same. However, when we iterate through our normal list, again, they're all in memory, in a vector, and accessible like that. And now that I think about it, these are contiguous, by the way. Otherwise, they couldn't be indexed. So that makes sense. Anyway, that's enough about that. Let's talk a little bit about uses for this outside of loops, right? So you can access any element in your list by using this syntax. So if I did this, I would be grabbing the 6th element because it's 0 indexed or 0 based. So the 5th element would actually be the 6th element in the list itself. Or using the number 5 results in the 6th element. Anyway, let's say for specifically this circle, I'm going to move it plus equals 20, comma 0. So what do you think happens here? Hopefully what you'd expect is that circle moves. So you can see we touched this circle, the 6th circle in our list, and it moved over 20 pixels. So just slightly overlapping the neighboring circle. What we did here, and what this operator does, is it grabs a reference. So we're modifying the item from the list directly. We're not creating a copy here. Now, I'm going to create a new variable called temp circle. You'll notice I'm not including the reference operator. And then I do this. And then I say temp circle.pause plus equals 20 pixels to the right. What do you think happens here? Well, from what we understand, if we don't include a reference operator, it's going to copy the circle, right? And that's what we should expect here. I'm going to add some bars here so we know we can look at the specific copy and creation of objects in this range right here. Just makes our debug output easier to look at. Alright, so as hopefully you've realized, we didn't actually touch this circle's position, unlike before. And that's because this temp circle becomes a new object that gets created. Look in between these equal signs, it says circle copied, which means this circle is not a reference to the circle at circle list 5, but a copy of said circle. And once again, if you wanted the circle specifically, you would include the reference operator here. So it's a circle reference instead of a circle copy. And now here, you can see the circle's position got modified again, and this time between the equal signs, there was no copying done. Since references are pointers, this also means we can use pointers. So what if instead I wanted to store a pointer to a circle? Well, first of all, a circle is not a circle pointer type. These are different types. If we wanted to use a pointer, we'd have to use the indirection operator to get the address of the circle at position, or the 6th element in circle list, index 5. And because pointers are a different type, they actually have a different operator for accessing members. You use the dash right arrow or greater than sign operator to access things from pointers. Let's check that out real quick. As you can see, the circle has moved once again, and no copying was done. So essentially what we're saying here is take a pointer, temp circle, and assign it to the address located at circle list 5. Temp circle's position, using this new pointer, is going to be added by 20. Pointers are simply just numbers, so we can also look at this. I'm going to create a reference again, ref circle equals circle list 5. And then I'm going to change this now to, say, pointer circle instead of temp circle. And I'm going to go ahead and output both addresses. So I'm going to take the address of ref circle, and I'm going to take the address of pointer circle. Alright, so you'll see here, once again, the circle changes. That should not be a surprise by now. But you'll see their addresses are a little different. What happened? I thought you just said that the reference is the address of it. Well, they are, but I actually made an error in my code. I'm grabbing the address of a pointer. And what happens if you do that? What does that actually mean? Well, somewhere in memory, my program has created a place to hold this number pointer. So it's not a circle, but it's a circle pointer, which is usually like a 64-bit address or something. How about we don't include the ampersand here? So we're not grabbing the address of an address. You'll see now there's two copies of the same exact number here, because they're both pointing to the same location in memory. These are essentially the same thing. So why would you use one over the other? Well, references are technically safer, because references have to reference some active object currently in memory. In case you didn't know, a pointer can be null, and a pointer can also be referring to an object that no longer exists in memory. And a reference could too, but a reference is a bit safer because you always have to assign it something. If I just did this, C++ is perfectly fine with that. You don't have to assign anything to it. But ref circle 2 here, if not assigned to something, will have an error. Why? References can't exist without pointing to some element in memory. If it doesn't exist yet, you can't have a reference to it. And I think this is a very important distinction, because pointers might not necessarily be valid on creation. References always have to be. And if you create some kind of struct or object that uses a reference, you have to specify said reference on creation. For example, let's say I have a struct called circle group. And a circle group will hold a vector of circle references. First of all, this isn't even possible. That needs to be down there. Secondly, when you create said items, since they have to be references, they have to exist in memory already. Let's utilize this structure real quick just to demonstrate what I mean. Let's make a new group called my group, and we're gonna push back into its circle list a couple of things. Let's push back circle 4, circle, I'm trying to think here what the list really looks like, 9, and let's push back circle list 3, or the elements of them. Then let's assign that to a new circle group. So I'm going to make a new vector called circle group list. So I want to be able to move all my circles, or certain circles, as if they were one unit. That's what I'm trying to do here. So I'll now push back this group of circles into my list. And that's fine, because each of these items already exists in memory. So if we have a reference to those circles, they get pushed back. And that's all well and dandy, because now when we go down here, when we go down here, I want it so my circle groups have a red circle around them as well. So inside each circle group, we'll iterate through its list of circles, which I'm also going to keep as references because I don't want new copies of them. And this is a little bit of a hack because I'm drawing twice. I would optimize this if I had more time, but I'm going to draw them with red outlines. Let's run this real quick. You'll first see we get an error. Pointer to reference is not allowed. So yeah, this is impossible. At least, not without a lot of additional changes. If you really want to store these, you would have to store them as pointers. And because they're pointers, you would have to include the reference operators here. And this is supposed to be... I kind of missed this. I'm gonna circle group dot circles. For each circle in the list, well, it's a circle pointer, right? So we get circle C, which means we have to use this operator for pointers instead. We can do this. So you'll see, for the circles located in the circle group now, they are red instead of white. And again, this is kind of a hack because I'm just drawing over what their original colors were. But for our demonstration purposes, it will be fine. Now I will take said circle group and I will move all the circles in that circle group by some amount. Again, I will, for circle group 0, which is the only circle group in my list, I'll take each circle's position and I will add 20 pixels to it. So all circles within that group get moved over. And you'll see that happens here. And as we know, since they are pointers, they are direct references to where they are located in memory. I hope this short little C++ fundamentals video gives you a little bit of insight into object creation and object copying. And just really kind of explains the intricacies behind using these. As a general rule of thumb, if you don't need to make a copy of something, you just have to use the ampersand operator so that you get a reference of whatever object you're trying to use. You don't really need a copy. You can start thinking about the copying details or semantics more while you're working on your programs. As usual, you'll find the repo to this code that we did today, plus the repo for the OLC Pixel game engine in the description if you need it. Thanks for watching.